We're going to do a couple more examples of determining moments of inertia. What's the moment of inertia for the thin ring at the right about its central axis? Whenever we find the moment of inertia, we need to integrate r squared dm. Now, for this case, here's a little dm right there. There's another one, there's another one, there's another one. Isn't it true that all of these dm's are the same distance from the center? And so what we can do then is we can say, oh, well, r is a constant, so we can pull it out of the integral, and then we just integrate dm. Well, what do you get when you integrate dm? You just get m. Normally, the m is written first. The moment of inertia of a thin ring about its central axis is mr squared. That was an easy one. The next one is a little bit more challenging. Here we have a disk that has a uniform surface mass density, and that's indicated by sigma. We met lambda a couple of videos ago, which was mass per length. Well, sigma is mass per area. So let's see if we can figure out this disk's rotational inertia about its central axis. The moment of inertia is the integral of r squared dm. Now, for a case like this, what is dm? dm is a really thin slice in here, much thinner than I'm able to draw. But that thin slice is a distance r from the axis of rotation. It has a thickness of dr. That's a dm right there. And we're going to integrate this from little r equals 0 to little r equals big R. We have a problem with the differential and the limits of integration not speaking the same language. So we definitely need to fix that. Now, how do we do that? Mentally, what we do is we take this thin ring. Imagine we could take it out and unroll it so it looked like that. So there's dm right there. That's dm. And it has a mass to area ratio of sigma. This whole disk does. Isn't this thickness right here dr? And what's the length of this piece? Isn't that just the circumference of that little hoop, which would be 2 pi times little r? So if sigma equals mass per area, this sigma is going to be mass per area, which means that dm is 2 pi sigma r dr. Whew, running out of space there. We're going quickly here, but hopefully you can follow this. We're going to substitute that into our expression now. We're going to go little r goes from 0 to big R, r squared times 2 pi sigma r dr. What are the constants here? 2 pi and sigma are constants. I can pull those out, which means we're going to integrate from 0 to big R, r cubed dr. And when we do that, we get 2 pi sigma 1/4 big R to the 4th. You check and make sure that all that's on the level. Now here's the deal. The mass of this, might have forgotten, let's go back up to the top of the page here. The mass is given. And the mass is going to be sigma multiplied by the area of the disk. Well, the area of that whole disk is pi times big R squared. So let's see. Pi, 2 of these r's, and a sigma. I can cancel that out. This 2 cancels out that 4. That becomes a 1/2. What does this boil down to? It looks to me like 1/2. Now watch this. The m takes into account that pi, that alpha, and 2 of these r's. mr squared. It's a little bit tougher than finding the moment of inertia of a thin ring about its axis. The good news is that these moments of inertia have been tabularized. So in most cases, you can just look up, hey, what shape do I have? What's the axis? What's the formula for the moment of inertia? Why will I, for a uniform cylinder, be identical to this? This one was a disk. Why will a cylinder have the same moment of inertia? Well, a cylinder is just a thick disk. We're going to do a few more examples of deriving moments of inertia so you can see how it's done. But as I said, the good news is a lot of these have been tabularized, so you can just look up the equation.